Today we're going to look at a second aspect of the new Applied Maths course starting in 2021. And what we have is part of the networks and graphs. This is a major part of the new course, about 20% of the whole course. And it's divided in the book in two chapters. So today we'll be looking at the first of those two chapters, which is called Networks and Graphs, not surprisingly. And there are some very introductory ideas. I'm not going to spend a lot of time, although they're dealt with very thoroughly in the book. But it is the difference between a walk, a path, and a cycle. And everybody who does the course must know this. A walk is where you have what we call nodes, which are just points or vertices, and they're joined with edges, or sometimes called arcs. And if you go from one to the other, to the other, to the other, without jumping, for example, if you went from A to B to C to A to D, that is called a walk. A walk is any continuous linking of nodes. I always remember W-A-L-K, by wander as you like, W-A-L-K. In other words, you can go anywhere, you can go back to A, you can go on, you can repeat things. A walk is any old continuous one, A to B to C to D. You could go A to B to C to D, back to A, then to C, then to B, then to D, then back to B. You can go, any of those are walks. However, a path is different. A path is particular about the nodes. In other words, you must never visit the same node twice. So P-A-T-H, particular about the nodes. So you go from A to B to C to D to E. That's a path. If you went from A to B to C back to A, that is not a path. You may never visit the same node twice. It's particular about the nodes, P-A-T-H. And a cycle is a path except for the last one, where you go A to B to D to C, but you must go back to where you started. That's a cycle, and a cycle is like a circle. In fact, the word cycle comes from the Greek word for a cycle, Kruskals. So if you go from A to B to D to C and then back to A, that is a cycle. Just to warn you that if you went from A to B to C to D to A, that is also a cycle, A to B to C to D to A, because the first four of them form a path, and then you're back to where you started. You can't visit the same place twice, except to the beginning and the end, of course, to get back to where you started. That is called a cycle. And again, all of that is dealt with thoroughly with exercises. I'm just going through the salient points here. The next idea is the idea of a tree. Now, a tree is a subset of a graph where everything must be connected. Now, connected would mean that you can go on a walk from any point to any other point, that it is possible on your graph to go from any point to any other point. And if it's connected, in other words, that you can go from any point to any other point or any node to any other node, and there are no cycles, then it's called a tree. And this, for example, is a tree. You can go from A to E. You can go from C to D. You can go from any point to any point, and there are no cycles. So that is a tree. This one, you can go from any point to any point. It is all connected, but there is a cycle, B to C to E to B to C to E. That's a cycle. Therefore, that is not a tree. The next one is not a tree because it's disconnected. You cannot get from A to B, no matter how. The last one is a tree because you can move from any point to any other point. It is connected, and there are no cycles. So that is a tree. So that's the idea of a tree. It's not a difficult concept. Again, it's dealt with in the book exhaustively with nice, simple exercises. The third idea is a spanning tree, and this is useful in everyday life. If you want to send an email to every one of your employees or to all your friends on Facebook without wasting money, you would like to minimize the amount of money you spend or the time it takes. How can you do it? Well, you use the minimum spanning tree. And the spanning tree for a graph G is a subgraph of G. So there's a graph. We get a subgraph of that, a subset of it. It must contain all the vertices, and it must be a tree. And here are some examples. There's P, Q, R, S, and T. That contains all the vertices of the graph above, and there are no loops, and it is all connected, so that's a tree. Here's another tree, a spanning tree for that graph G, and here's another one. I could draw another one if you went from P to T to S to R to Q. That is also a spanning tree for going from P to T to S to R to Q. That is another spanning tree. And spanning trees are important in everyday life, as we shall see. Now, what's very important is to find the minimum spanning tree, because now the minimum meaning that the weights are the least. Now, the weights could be the cost, and therefore we want to lower our costs. The weights could be distance, and we want to minimize our distance. The weights could be the time it takes to send an email from D to B, and we want to minimize the time. So how do we get the minimum spanning tree? A very important task. Well, there are two important algorithms for this. The first is Kruskals algorithm, and it is very straightforward. Kruskals algorithm, you can start, you always start with the arc of lowest weight. So we look at this. I'm just going to zoom in on this a bit closer. And I'm going to get it to focus. And now I'm going to look at my arcs, and I see that the one with the lowest weight is the arc from D to F, which has a weight of 5. So there's the first arc in my spanning tree, DF. Now I keep adding the arc of lowest weight, except I must never create a cycle. If adding an arc creates a cycle, you don't add it on. Then the next weight, the lowest weight is 6, and therefore I'll add that in. So now I have B to C. I keep going. 6.2 is the next one. I'm just being very careful not to. No. Now, if E to F was 6.3, I would not add it in, because that would create a loop. So you just simply keep adding the edge of lowest weight until you get your spanning tree, but you must never create a cycle. Now, I'm going to continue on with this. The next one is 7, and that does not create a loop, so I add C to E. The next one is 8, but if I joined 8, I would create a loop, so I don't do that. The next one would be 9. That would create a loop. If I joined B to D, I'd have a cycle there, B to D, so I don't add that. But this one I can add without creating a cycle. And the only one now to be joined is G, and at the lowest weight, 10 would create a cycle. So but 9.8 is the lowest. And now I have every node is joined, and I have my spanning tree. Now, in order to make this what you did clear, what we usually, that is the job. I had D to F, then B to C, then C to E, and so on. I just list them out there. But in order to be very clear, there is a system that we like to use, which is to write down the weights of each, and I put them in alphabetical order. That's D to F. This is just a way of representing what I did above and making it a bit clearer to an examiner what I'm up. The next lowest weight is 6, and that is the weight from C to B, or B to C if we use alphabetical order. The next is 6.2, and that was from D to E. And the next shortest arc was C to E, which is 7. After 7, we have one of length 8. That's C to D. We have 2 of length D, B to D, which is 9. And there was another of length 9, A to C is of length 9. Then we had 9.8, E to G. And then we had, after 9, we have 10, A to B is of length 10. And then we have 2 of length 11. They are E to F and F to G. This is another way of representing it. So I include that one. Then I included BC. Then I included DE. Now, C to E, yes, I included that. Now, joining C to D would have created a loop, so I simply cross it out because it would create a cycle going from D to E to C to D to E to C. So I cross it out. B to D, going from B to D would create a square cycle there. That is not allowed, so that's not allowed. A to C was included. E to G was then included. A to B would create a loop, and E to F are not needed. So I've got those ones. And if you want to work out the total length of your spanning tree, you simply add up 5 and 6 and 6.2. Well, I'm going to start by adding 6.2 and 9.8 because they add up to 16. 16 and 11 is 27, and 9 is I'm not sure. I'm going to use the old calculator just to be certain here. 5 plus 6 plus 6.2 plus 7 plus 9 plus 9.8 is 43. The total length of my spanning tree, my minimum spanning tree, using Kruskals' algorithm is 43. Having this shows your work, and that's what's advantageous to it, to just drawing it like that. And so I think this would be, this is expected as the method of showing your work. Now, I'm going to use an example from real life with 2 variations. And here I go. Wicklow County, this is a question from the book. Wicklow County Council has decided to link 8 villages with 2-way cycle lanes so that people can cycle from any of those villages to another. They have promised that you may be able to cycle from any village to another. The cycle lanes must be along the existing roads which appear on the network. So these are the existing roads, and we're going to put the cycle lanes at the sides of these. Find the length of the minimum spanning tree. Well, the minimum spanning tree would mean that you may cycle from any of the villages to any others. So I'm going to use the table because that shows my work, and I'm going to go ahead. Here I go, from F to G is 4.4. I've written them down, the lowest up to the longest of all the arcs. By the way, I must mention that when you come to a point where there are 2 of equal length, it actually doesn't make any difference which one you do, as long as you don't create a cycle. You can include either one, and if you include one and then the other one has to be left out, you will find that you get 2 minimum spanning trees, but they will have the same length. In other words, you have choices sometimes, and the decision, there can be more than one correct answer. But they will have the exact same length if I did another one, and there are examples of this in the book. Find the length of the minimum spanning tree here. Okay, well, we'll include F to G. It's 4.4, and that's the first arc in my spanning tree. C to H is 4.8. I'm going to include that arc. No loops have been formed. E to H is 4.9. That's lovely, no loops. C to E, if I do C to E, I create a loop, so I cross that out. That is not to be included. D to G does not create a cycle or a loop, so that's included. E to G, no, that would not create, that's 5.3, that's in. A to F, no evil work done by including A to F, that's in. There are no cycles yet. A to D, now A to D would create a parallelogram cycle there, A to D to G to F to A to D to G to F, not allowed. No cycles allowed. D to E, D to E to G would form a cycle, not allowed. D to F, not allowed. Again, there would be a triangular cycle there, not allowed. B to C, there's no putting in B to C at 6.9, that's okay. And A to B, no, if I do A to B, I'll have a loop. The whole way around, the whole thing would be a loop. Sorry, a cycle. No. So, what is the length of that is my spanning tree. I've drawn it up there, my minimum spanning tree, or MST. And 4.4 plus 4.8 plus 4.9 plus 5.2 plus 5.3 plus 5.7 plus 6.9. $37.2. Now, I'm going to, what is the cost? Next question, what's the cost of creating this network if cycle lanes are that's 1,450 per kilometer? Well, I simply multiply my answer by 1,450. And I get the cost is 5,3,940. 53,940. I hope all my maths is correct. Now, interesting variation. If the cycle lanes from A to F and from E to C have been already exist and have been paid for, then what is the minimum cost of completing the cycle lane network? Well, I'm going to start again, but I'm going to include A to F, but I must remember not to include them in the total. I just put a bracket around them because they're already paid for. And E to C, yeah, they're already paid for. And now I'm going to write down the other ones, 4.4, 4.8, 4.9, 5.1 is, I have that already, 5.2, 5.3. I'm not putting in 5.7, that's above 5.8, 6.1, 6.2, 6.9, 7.8. And I'm going to use this for the total. Is that all visible? Beautiful. 4.4 is F to G, 4.8 is C to H, 4.9 is E to H, 5.2 is D to G, 5.3 is E to G, 5.8 is A to D, 6.1 is D to E, 6.2 is D to F, 6.9 is B to C, and A to B is 7.8. Let's create the minimum spanning tree. Now, we've already created these two arcs, so they're definitely in and don't have to be paid for. Can we add in 4.4 without creating a cycle? We can, so that's in. C to H is 4.8. That could be added without creating a cycle. That's good. E to H at 4.9, that would create a cycle, so that's crossed out. D to G at 5.2 would not create a cycle. It would be there. So I'll fill it and include it in. E to G, yeah, E to G would be okay. No cycles completed by adding it in. A to D, that would create a parallelogram cycle. Nope, not allowed. D to E, not allowed because we'd have a triangular cycle. Not allowed. D to F, no, that would give you a triangular cycle here. Not allowed, sorry. B to C at 6.9. Yep, that's acceptable. And A to B definitely not, because then we'd have a huge big cycle. So the spanning tree is, I don't have to pay for that, I don't have to pay for that, so I only have to pay for. Let's use the calculator. 4.4 and 4.8 and 5.2 and 5.3 and 6.9. That's all I have to pay for. That as a decimal is 26.6. So that's the length of the number of kilometers at 1450. So I shall multiply that by 1450, and the cost will be 38,570 euros only. Brilliant. Very simple, and you can, if I build that now, and you can cycle to your heart's content. Now, Prim's algorithm. Now, it's very important to understand that it does the exact same job. It finds the minimum spanning tree. So it's just an alternative way of doing it. But it does it in a different way. You're told usually to start with a point. Now, it might ask start at B. So we'd say start at B. If it doesn't say start at B, you can start wherever you like, and you'll get the same answer wherever you like. And Prim's algorithm brings you to the nearest point, the nearest node. Now, if we include B, the nearest nodes are C, which is 10, F, which is 7 away, and A, which is 8 away. Well, the nearest of those is F. So there's my first. I go from B to F. Now, that's my tree so far. If I were to add, now I look for the next nearest node to anywhere on my tree. Well, now because I'm at F, I could go to A, which is 4, to E, which is 5, to D, which is 7, to C, which is 5, and also I still have the 8 and the 10. Well, the nearest node would be A, so I add in F to A because that's of length 4. Now I look at my tree, which is B to F to A, and I say, what is the nearest I can get? And the answer is either of these 5. Now, it does not make any difference. This is the same, which decision you make. If you decide, so there can be more than one correct answer, but they will have the same total length. So I'm going to do C to F because it's of length 5. And now I look, and my spanning tree goes from B to F to C to A, and I say, what other point can I link in that's as close? Well, E would be 5 away, but D can link to C with adding only 4. So I'm going to link D because it's the nearest point to my spanning tree. C to D. Now, I've only one more to go, and again, I must not create a loop. I must never create a loop or a cycle. And my last one is F to E because it's 5, and now I have linked all of the points, and that's my spanning tree, F to E. Now, the total weight of that is 7 and 4 and 5 and 4 and 5, 16, 25. That's the answer, 25, whatever, 25 units. They could be units of time, units of money, units of distance. Now, how do you represent that? Well, that would be acceptable. That is Prim's. Now, the difference between Prim and Kruskal is this. Kruskal adds the shortest arc. And along the way, Kruskals is not always a tree. Sometimes you have disconnections. Prim adds the nearest point to your tree, and Prim is always a tree. At any stage while you're building up using Prim, you have a tree and you add the nearest point. So I always remember K and K. Now the correct spelling for arc is ARC. ARC means a line segment, or another word we use for it is an edge. But just for the point of this, to remember it, I say Kruskal adds the nearest arc, or the shortest arc, and Prim adds the nearest point. And Prims will always be it will always be a tree as you move along. Now, there is another way of representing Prim's algorithm what we've just done would be an acceptable answer. We showed the order in which we added the nearest point, and we showed their distance, so that's perfectly adequate. That's the answer to 1, and that's the answer to 2. But there is a matrix fashion. If we have A, B, C, D, E, F, and A, B, C, D, E, F, we can say from A to B is 8. So from A to B is 8, and obviously from B to A is 8. So it's a symmetrical matrix. From A to E is 11. From A to E is 11, and obviously from E to A is 11, and so on. So we have a matrix. It is possible, if you are simply given that matrix, to perform Prim's algorithm without using a drawing. And here it goes. It's a bit contrived, but here I go. I'm going to start at B. It says in the question start at B, so I'm just going to start at B. So what you do is you cross off B because you're starting at B. B is already regarded as on. And you write that the first one, you put a 1 over the B. Now you will begin to see the connection when you look above and see what, this is just a very contrived method of doing what we did above. You look down under the number 1. There's an 8 and a 10 and a 7, and you pick the smallest ones. The blanks mean there are no links from B to, say, D, or no links from B to E. That is my first link from B to F. So B to F, that one is squared, and that counts. Now I cross off, because I have chosen F, I cross off F's line, apart from the one that I chose. And F is my second node on the spanning tree. Now what do? To get my third one, I look down both lists, 8, 10, 4, 5, 7, 5. And I say, which is the smallest of them? Well, the answer of 8, 10, 4, 5, 7, and 5, the smallest is 4. So I'm picking 4, and that's going to A. Because it goes to A, I cross out row A, except for the box, and I say A is the third node on my spanning tree. Now I look down all 3. Under A, I have 11. Under B, I have 10. And under F, I have a 5 and a 7 and a 5. Now, which of those is the smallest? Whichever I like of these, it makes no difference to the answer, although you will have a different spanning tree. But I'm just going to take the first one here, C to D. That brings me to C. So C is the 4th on my spanning tree, and I cross out the row C, except for the one that's boxed. Now I look down all the ones with numbers. Under 3, that's A, I have 11. Under number 1, I have nothing available. Under C, I have 4. And under 2, that's F, I have a 5 and a 7. Well, of all of those, the shortest is the 4. And that brings me to D. So D is the 5th node on my spanning tree, and I cross out D apart from the box. But the last one is E. So I look down under all of these, 11 or 6 or 5. Well, 5 is the smallest. So I have 7 and 4 and 4 and 5 and 5, which adds up to 25 again. That is using the matrix method. Here's a problem that uses the matrix method from the leading cert. The matrix shows the distances along direct roads between 6 towns in Wexford. Use Prill's algorithm to find the minimum connector. That is another word for the minimum spanning tree. And you have to start at A. If we start at A, we cross out A. We look down under A. The smallest is 13. A is number 1. We get 13. So that is the first number in our spanning tree. So F, we cross out all of F, and F is the second in our spanning tree. We look under both lists, 12 and 14 and 15 and 17.5, 19, 21, 20, 17. The smallest under both of those lists is 14, which brings us to C. So C is the third node in my spanning tree. I cross off C, and I look under all the numbered lists, 21, 15, 17.5, 16, 20, 24, 19, 20, 17. The smallest of those is 15. And that brings me to D. That's the 4th on my spanning tree, so I cross off those. Now I look under all lists: 21, 17.5, 16, 24, 22 and 19, and 19 and 17. Only the numbered lists. The smallest number in the numbered list is 13, which brings me to is 16, which brings me to B. So B is the fifth node on my spanning tree, and I cross off B apart from that one. Now I look under all the E is going to be the sixth. I have 17.5 or 18 or 24 or 17. That would be the next one, which brings me to B. So that is the last one. So the spanning tree is, the length of it is 14 and 15 and 13 and 16 and 17, which gives us 75. So that's the length of the minimum connector or the minimum spanning tree. And the next question asks, after a snowstorm, Wicklow County Council decides to clear the road so that anyone can drive from any of these towns to the other. What's the minimum length needed? Well, the minimum length will be the minimum spanning tree, because that allows you to travel from any of these to any of these, as we saw earlier. And so that will be 75 kilometres. Wicklow County, or is it Wicklow or Wexford? Wexford County Council approaches two companies who submit tenders to clear the snow. The first will do the entire job for 1,000. The second charges 15 euros per kilometre. Well, if we multiply 15 by 75, we get 15 by 75, every student's best friend, 1125. So it's cheaper to do 1,000, the 1,000 entire job. So the first offer is better. The first offer is better of 1,000, because 1125 is a bit too much for the Wexford County Council to spend. So that is Kruskals' algorithm and Prim's algorithm put to very good use in Ireland. Thank you.